Okay, good afternoon. Today our topic is about the Fourier series. So this is your Fourier series. Okay, you pronounce this as a Fourier series. So Fourier series now is used in periodic functions. Okay, now Fourier series is used in periodic functions. But what is a periodic function? So if I have here, now when we say periodic functions, it means, when we say periodic functions, it means that if your function of t is equal to your function of t plus your period of time. So t here is your period. So period is the time when the continuous time signal repeats itself. So periodic function. Okay. Like for example, if I have here a simple periodic function, let's say I have here a simple periodic function. Okay. Let's label this as your sine wave. Let's label this as your function of t equals to sine of, let's say, omega t. So omega there is your radian frequency. Okay, when we say period, it is one complete the time that your graph will have one complete cycle. This is one complete cycle. So what is the time there? So the time now that the graph or your function completes a cycle is what we call your period. And period here is equivalent to 1 over the frequency. Okay, take note of that. This radian frequency in omega, let's say omega. So omega here is just 1 over, that is equal to 2 pi of the frequency. Or in terms of period, we label this as 2 pi over your period t. That's how you label your radian frequency. Take note. This is one period and another period is here. So this is called periodic functions because so when time equals t, assuming this is time equals t, what is the value here? So the value here is this value. Okay, let's label this as f of t. That's your value. Now, after one period, let's label this as one period, one complete cycle. Now, you have the same value after one complete cycle. That is why we call this one your periodic functions. Now, later on, I will show you what are those periodic functions that are common to engineering. Okay. Now, I will erase this part first, and then we will continue with periodic functions. Here are some examples of periodic functions. So I have here my sinusoidal function. Let's label this the sine wave. So for the sine wave, this will be your function. So let's label this as your sine wave. Okay. For your sine wave, let's label this your function of t. And this will be your function of t equals to, let's say, a multiplied by sine of omega t. Take note, a here is your amplitude. This is your a. A here is your amplitude of sine. And then the period for your sine is the time when your function completes one cycle. So we call this your period, or you can label this as 1 over the frequency. And we know that omega here is equal to 2 pi of the frequency, or shall we say 2 pi over the period. So that's how you analyze later on the parameters of sine. Okay, this is the sine function. Now we go to the cosine function. So we will call this one your cosine wave. So for cosine wave, okay, I will make it smaller. So this is your cosine wave. Cosine wave is actually your sine wave, but it is delayed by 90 degrees, okay, or advanced by 90 degrees. So you can have this as your function of t, which is equal to function of t is equal to cosine. Let's label this as a cosine of omega t. A here is your amplitude. Okay, note the graph will actually move from negative infinity up to positive infinity. So your period here is the time when this cosine function makes a complete cycle. So let's label that as period equals to 1 over f. Of course, the amplitude here is equal to a, and your omega here is the same, that is 2 pi of the frequency, or 2 pi divided by your period. That's how you analyze the parameters of the cosine function. Let's have another type of function. This time, I will give you the square wave function. Okay, the square wave. When you say square wave, this is very common in our electronics subject. Okay, let's label this as function of t, and this is your t. So square wave, so this will be the representation of my square wave. I will be using different color. Okay, this is the representation of my square wave. Alright, that is your square wave, and your period is from this point up to this point, because this will be one complete cycle of your square wave. So that will be your period. So let's label this as t, and we will label this as, of course, the amplitude a. So this is your square wave. We also have, okay, by the way guys, these are the periodic functions. Now, we also have the triangular wave. The triangular wave. When you say triangular wave, so it is, it forms like a triangle. So this is your triangular wave. Okay, that's your triangular wave, and your period will start from this point up to the end of your one complete cycle. So this is your period, which is also equals to 1 over frequency. Take note when you say period, the unit for period is, what's the unit for period? Okay, period means, when you say period, okay, the unit is in seconds. Seconds per cycle. Seconds per cycle. So we need to say 1 cycle per second. That's your period. That is equivalent to hertz in frequency. So for the frequency, this is just 1 over period, or shall we say cycles per second. Okay, cycles per second is denoted as hertz in our electronic subject. So this is hertz, cycles per second. That's for the frequency, and for the period, that is seconds per cycle. Alright, now we have the sinusoidal wave, the square wave, and the triangular wave. Let's move on to another types of wave, of periodic waveform. Okay, I have here the sawtooth wave. Sawtooth wave, so that's for letter E. Letter E, sawtooth wave. So when you say sawtooth wave, now it will look like this one. Okay, I'm sorry, let's erase this part. So this is the sawtooth weight. Okay. To make it simpler, that is your sawtooth weight. So meaning to say, this will be your maximum or peak or the amplitude, and this will be your period. So this is your period t, and that will be your amplitude. So this is your function of t, and this will be your time. That is your sawtooth weight. So another waveform, this is also, the sawtooth weight is used in creating a type of waveform that is pulse width modulation wave. So later on you will encounter this in your higher electronics subject. Alright, now we also have the full wave. So when you say full wave, this is your full wave. This is actually your sine wave. That is okay, this is your sine wave. This is your sine wave. And your full wave is this one. So a full wave is actually the absolute value of your sine wave. So the red one is your full wave. So you can represent this also as function of t equals to the absolute value of sine omega t. When you see absolute value, all values are positive, meaning for sine functions that are negative in values, so taking the absolute value will become positive. So meaning to say this will be your what they call that, waveform. And of course your period now will start from this point up to it completes one cycle. This is one cycle, another cycle. Okay, that is your period. That's for your full wave. Okay, full wave is used in electronics, especially in your topic ng power supply. Of course, now we also have letter E, letter G. Let's label this as your half wave. When you say half wave, this is actually a full wave, but half of that only. So this is your half wave. This is your half wave. So half wave, okay. Okay, these are the peak of your what? Half wave. So we need to say we can label this as your amplitude. Of course, this is also the amplitude for your full wave, and the period can be calculated using this one from this point up to that point, because this is your half wave, one complete cycle. So another cycle, another cycle. So that will be the period for your half wave. Okay, any questions about the waves? Any questions about the waves? This is very important because later on you will encounter all of these types of waves, and shall I say these types of waves have a complicated Fourier series. Alright, now we go to the types of symmetry. So the types of symmetry is also important when dealing with the Fourier series, because it will help you save a lot of time, especially in solving the series. Alright, now for the symmetry, when you say types of symmetry, so these are the types of symmetry of your function. When you say even symmetry, let's start with even. So even symmetry if your function of t is equal to the function of negative t. So if I'm going to represent that as a graph, this will be your function of t, and this will be your time. This is your graph. Let's say this is your graph. Okay, and this is your function of t. So let's label this as your function of t. Okay, now what does it mean when you say even symmetry? Uh, Even symmetry means that the value of your ft, okay, like assuming this is your time t from the origin, the value of your ft, no, if t is equals to this value, will also have the same value for negative values of t. Okay, that's how you represent your symmetry. Meaning to say, in short, even symmetry now will have the symmetry across along this point, along the y-axis. So when you say even symmetry, meaning you can actually cut the function now identical from left to the right. That is your even symmetry. Examples of even symmetry. So we have here examples of even symmetry. Examples of even symmetry. I have here the cosine function. So this is your cosine function. Okay, this is your cosine function. Okay, let's redraw it using the other color pen. So this is your cosine function. So cosine function will start from there. Okay, that is your cosine function. Okay, that is actually your cosine function. So cosine function is symmetrical along your y-axis. This is your function of t, and this is your t. This is the axis of symmetry. So meaning to say, the axis of symmetry will divide your function identically into two. So that is your axis of symmetry. So these are the examples. This is your function of t equals cosine of t. Okay, example number one. So let's have another example here. Let's say I have here a square wave. So this is a square wave, no? And it is symmetrical to your y-axis. But let's label this as your y-axis. So this is the axis of your symmetry. When we say axis of symmetry, or AOS, this is the line that divides your graph into two identical parts. Any questions with the axis of symmetry? No more. So take note of this. This is very important when dealing later on with complex to make your Fourier series application easy. Okay, that is for even symmetry. What about for your odd symmetry? So I can erase this part first. For the odd symmetry, when we say odd symmetry, okay, this is your odd symmetry. When we say odd symmetry, your function of t is equivalent to, your function of negative t is equivalent to negative of function of t. So what does it mean? It means that if I have here another function, let's say this is my function. Okay, this is my function of t. This is my function of t, which is also a periodic function. What does it mean when I say a function of negative t? Function of negative t is equals to negative function of t. It means that when the time is negative, let's say this is negative t, the value here will be negative of the value that we get at that point, where t here is positive. So meaning to say, the value here is positive f of t, and the value here is negative f of t. But definitely they are numerically equal. Okay, that is how you emphasize the odd symmetry. Now, here are examples of odd symmetry. So when you say odd symmetry, that is symmetrical to your origin. When you say symmetrical, your origin will divide your graph into two equal parts. Okay, now for example, I have here my sine function. this is my sine function. When we say sine function, this is the graph of your sine function. Okay, this is the graph of your sine function from negative to positive infinity. Okay, that's the graph of your sine function. This is y, or this is function of t equals to sine of t. So now if you will notice that once the value of t increases, okay, the value of t increases, another value, the value of negative t here decreases. So that is the property of your odd symmetry. So another type of symmetry using the square wave is this function. Let's say I have here this waveform. Okay. Let's follow it red. This is my odd symmetry wave, square wave. So this is your origin, and when time is approaching this value, okay, the value is positive. When time is approaching this value, the value of f is negative. So that is an example. These are examples of odd symmetry waveform. Okay, any questions with odd symmetry? So feel free not to comment on this video for your questions. All right, now we go to the representation of your Fourier series. So technically, all continuous, all periodic functions are can be represented by a Fourier series. What does it mean? Meaning to say, all of the elementary waveforms that I sketched a while ago now can be represented by the Fourier series. Okay. Now, mathematically, your Fourier series can be written as, so this is your Fourier series. Okay, so mathematically, your Fourier series can be written as your function of x. Okay, instead of x, I will be using function of time. So function of time is equivalent to a0 over 2 plus a sub 1, okay, cosine of omega t, let's label that as omega t, okay, plus a sub 2 cosine of omega 2 times t, okay, and so on, plus for the component, the side component of the function, we have sine omega t plus b sub 2 sine of omega 2 times t, and so on. So this is the representation in series of any periodic functions. Take note, Fourier series is only used for periodic functions. Alright, so that is the application of Fourier series in periodic functions. So mathematically, Fourier series now can be written as, okay, it can also be written in sigma notation. This is a0 over 2 plus a sigma notation from n. Take note, we started with 1 up to n equals infinity of your a sub 1. Let's label this as a sub n cosine of n omega 0 times t plus b sub n sine of n omega 0 times t. Okay, now when we say omega 0, this is your fundamental frequency. Okay, this is equivalent to 2 pi f of 0, or shall we say this is 2 pi over the period t. So f0 is your fundamental frequency. Okay, that is very important, the fundamental frequency. And of course, an and b sub n are just your coefficient. coefficient of your Fourier series. What about A0 over 2? A0 over 2 is your average value. Average value in electronics, we call this one your DC value or DC component. Okay. Okay, this is DC component or your DC value. Okay, that is in electronics. All right, now how about A sub n? Take note. What about n? So n here is an integer. So meaning to say the value is from 1, 2, 3, 4, 5. So these are positive integers. Okay, that's for your Fourier series. Now take note, your Fourier series mathematically can be expressed using this series or this sigma notation. Alright, now to solve for A sub 0 over 2, this is just your period or the area under the graph divided by your period t. Or using the integral calculus, we have integral 1 over t times the integral from 0 to t. Take note of this. Take note of the limits of your function of t dt. This is how you calculate your average value. Take note, this is very important to calculate your average value because this is part of your Fourier series. Also, we have A sub n. We can also calculate A sub n, that is 2 all over t times the integral from 0 to t. From 0 to t of your function of t multiplied by what? Right, multiplied by cosine n omega 0 times t multiplied by dt. This is also important because later on you will be solving a lot of A sub n and B sub n. So for B sub n, this is the coefficient of your cosine terms, while B sub n is the coefficient of your sine terms. So this is 2 over t integral from 0 to t function of t multiplied by sine n times omega 0 times t multiplied by dt. Now you have to familiarize all of these formulas. When I say familiarize, you need to use this frequently so that it will be part of your system. Oh, now, why do we need to solve the Fourier series? Where are we going to use this series? Okay, that's a good question. Okay. Now, the applications of Fourier series is very simple. It actually represents you are going to convert. Fourier series is actually converting the time domain into your frequency domain. Later on, I will show you the applications of Fourier series. So, like for example, I have here. Okay, here are some examples. Okay, assuming I have here my function of t. So let's label this as your function of t, and this is your t, and this will be your waveform. So this is the waveform. This is a pure sinusoidal wave. So I will not be drawing it anymore. So this is a pure sinusoidal wave with amplitude of 5. Okay. Now I will label this as your function of t equals 5. Then this is a sine of, let's say, 2000 pi multiplied by t. When we say 2000 pi, it means this is your omega. So omega is 2000 pi, which is 2 pi times 1000. 1000 here is your frequency. So this is very important because we can actually extract the frequency here and later on sketch that in your frequency domain. This is your time domain, and this is your frequency domain. When we say frequency domain, this is your frequency versus your amplitude or power. In this case, we will be using the amplitude. So this is frequency, okay, in hertz versus the amplitude. While in time domain, that is time versus the amplitude. Okay, now, how are we going to translate from this time domain to your frequency domain? So we will translate this to this. All we need to know is the magnitude and the frequency. So in this case, what is the frequency here? Only 1000. So if I have here 1000 as my frequency, okay, and of course, now this will be my amplitude, which is also 5, which is 5. Now I can represent a pure sinusoidal wave into this type of waveform in frequency domain. So this is just one vertical line with maximum amplitude of 5 as represented by the amplitude there, that is 5. Now if I have 2 or more functions, definitely 2 or more frequency, definitely I can draw each of that functions. Later on I will show you. Okay, now let's have another example. This is example number 2. Assuming now the waveform is shifted 5 units above your origin. This is your origin, and this is your 5, and the amplitude now becomes 10. And the maximum is now 10, not the amplitude. Now if we are going to draw this one, if we are going to translate this waveform into its equivalent frequency domain, okay, how are we going to do that? What do we need? So we need the frequency and the amplitude, of course. We need the frequency and the amplitude. Okay, now if I'm going to label this as your function of t equals to 5 plus 5 sine of, let's say, 2000 pi t, we know that your frequency is, from this, your frequency is equals to 1000. Do we have another value here? Yes, we also have a frequency of 0 as represented by 5. Okay, so 5 here is constant. Definitely, for a constant, the frequency is 0. Now we can translate this time domain into frequency domain. Now take note, we have here frequency of 1000, okay, assuming this is 1000, and the amplitude here is 5. So this is your frequency in hertz. Another frequency we have 0, which has an amplitude of 5 also. So this is your amplitude. Alright, now that's how you represent your time domain functions into your frequency domain functions. What about if I have multiple values of sine? Okay, now I will not erase this because this will be our guide later on. So what is important here is, from this graph, we know that the average value, here is your average value, 5. How do I know that 5 is the average value? By inspection. The average value is the value, if we are going to add the maximum and the minimum and divide it by 2. Let's say 10 divided plus 0 divided by 2 is equal to 5. That will only work for some functions, not every functions will work on that. Okay. Now, you will notice that the average value of 5 here will have a frequency of 0. This is actually your average value. 5 here is your average value. Take note of that. Average value have a frequency of 0, meaning to say, when you say average value, that is your DC component. Your DC component or your battery or your cell have a frequency of has a frequency equal to 0. Alright, now let's have another one. This time I will be using multiple frequency. So let's label this as number 3. Let's say I have here function of t equals to 4 plus 6 sine of 1000 pi t plus 3 times sine of 500 pi t. Now we are going to translate that to your frequency domain. How are we going to do that? If we are going to translate this to frequency domain. So all we need to know is some information about the frequency. What's the frequency here? So this will become 2 pi times 500. So 500 is the frequency here. What about this one? What's the frequency? Right, that's 250. That is 2 pi times 250 hertz. The frequency here is 0. Alright, now if we are going to sketch this in a frequency domain, this is your frequency versus your amplitude, or a frequency of 0, what is the amplitude? 4. So for a frequency of 0, the amplitude here is 4. Okay, now for the frequency of 500, okay, assuming this is my 500, the magnitude is 6. Magnitude or amplitude? We can label it as magnitude. What about for the frequency of 250? Now for 250, that is 3 as the amplitude. Now that's how you draw your, that's how you translate your time variant function, time varying function to your frequency varying frequency domain. This is your frequency domain. Okay, any questions with this? Because later on, now we are going to solve, we will be solving the amplitude and the frequency of your function, of your elementary function. Now I think we will start with taking the Fourier series of your square wave. Okay, taking the Fourier series of your square wave. A square wave, no, is actually when we are going to synthesize the square wave. Okay, this is your Fourier series of some elementary function. Let's start with your square wave, because a square wave is a function that can be easily solved, no, using the Fourier series, using these equations, using those formulas. Okay, let's start with your square wave. The square wave. Okay, this is your square wave. Let's label that as T and your ft. And okay, I will label this as my square wave. Okay.